We should be on chapter 7. We should all have given a little bit of chapter 7 our love and undivided attention. So chapter 7 it is. This is interactions with matter. Now, I know that this is going to be very simple, and I want to make sure that I take this very detailed. But can someone, you didn't get the PowerPoints? I haven't sent y'all the PowerPoints? Oh, well, let me do that now. Thank you. Okay, I'm sending it now. It's just that I had already put a lot of graphics on this, and it's taking a little bit. So some of the graphics may come over, some of it may not, but you can follow along at least with the information. Okay. Okay. Now we're back. Thank you, Jessie, for letting me know. All right, so we are here. We are in chapter 7. So when we're thinking about matter, I want anything that takes up space, weight. We talked about the units of measure. What is matter? Matter is anything that takes up, that has mass to it, has weight to it, takes up space. So when we're thinking about that, I want to make sure that we understand when we're talking about matter, we're not talking about tungsten atoms inside of the tube. We're not talking about molybdenum inside the tube. We're not talking about any of that matter. The matter that we're going to start talking about is human tissue. We're talking about the body. We're talking about X-ray has now left the beam in its primary form. It's a primary beam and is now going to interact with human tissue objectives. Okay? Questions about that? I want to make sure that we all understand what we're talking about when I say the word matter. We are leaving the tube. Okay? So now let's take a quick review. I'm going to voluntold here as Bethy. When we think of a photon, what are we saying? What's the AKA other word for photon?
X-ray.
X-ray. And I really want you to understand what I'm going to be talking about, because we're going to have electron and side by side with photon. That was a little bit different because when the tube, we talked about incident electron, which meant what, Amy? If I said incident electron in the tube, what was the other word for incident electron? What else did we use? Where did it come from?
They come from the cathode.
What specifically in the cathode?
The electrons.
I know. Well, where specifically in the cathode did these electrons boil off from?
From filament.
Thank you. So they were called filament electrons, and then they became incident electron when they collided with another electron inside of the focal spot. Make sense? Good. So in this chapter, you are going to have to keep it straight. We are talking about a photon coming in. So you're going to hear the words incident photon, just like we heard incident electron. Okay? So where does the incident photon come from? The primary beam. So the incident photon is in the primary beam. Make sense? So then we're also going to enter incident electron, which we've heard that term before, but we were used for it to come from a cathode or a filament electron. Not the case here anymore. We've left the filament behind. The tube is up there. we're now talking what's going on in here. I want to also go over symbols. But before we do that, what process is this, Tracy? When I look at this image, what is this a process of? What is this a picture defining what process? A photon comes in, an electron goes out. What does that represent? One word, starts with an I.
Interaction.
Yeah, it's an interaction, but it's more or less, Aurora, help her out.
Ionization.
Ionization. So when we think about ionization, we have a photon coming in, or even if we had it inside of in the tube under characteristic, we had an incident electron coming in and an electron going out. Anytime we remove an electron, it is ionization. Got it? But this time we are doing ionization with photons, not incident electrons. Okay? So the symbol for photons is this sine wave. S-I-N-E wave. It's a sine wave. So it's going to give you this little symbol. So when you think of a photon, there's no positive charge, there's no negative charge, there is no mass, there is no weight, there is none of that. It is a bundle of energy traveling, and it travels in a wave. Got it? So photons travel in the primary beam in a waveform, just like this. So what is the symbol? It's a sine wave. S-I-N-E wave. Got it? Everyone good with that? Good. So photons have no charge. Photons have no weight. Photons don't have any of that. Okay? They're just bundles of energy that's traveling in waves. Okay? Now, here, what is this a picture of, Daniel? What am I looking at right here? If you had to label this picture, what am I looking at?
Is that the shell?
Well, these are shells. These are electrons. These are protons and neutrons. So what is the entire thing?
An atom.
Start with an A.
Atom.
Atom. So we have a photon entering the atom, and here we have an electron going out. The symbol for protons in this chapter is going to be the positive, and the electrons are going to be the negative. So why is this important? Because I need you to pay attention to the images. The images speak volumes. The images are telling you the type of interaction that is happening. Just like we did from Bremsstrahlung and characteristic. You looked at the images to determine which interaction happened there. Was it a Brem X-ray or was it a characteristic X-ray? Make sense? So the pictures mean a lot. Any questions on this review? Okay. So we're talking about objectives, and I found this image, and I want to make sure that you understand we're leaving the tube behind. We're not talking about effective focal spot. We're not talking about actual focal spot. We're not talking about cathode and anode. We have left the collimator assembly. We are now using the primary beam, and we are interacting with matter down from the atomic level. So down to our very core of makeup, we're talking about photons interacting with these atoms. Does everyone understand what I'm saying? Okay? We no longer know the K-shell binding energy. We no longer know how much KVP is going to cause to remove an inner shell electron, because this atom could be calcium, this atom could be hydrogen, this atom could be nitrogen, this atom can be anything. Make sense? Yes? Thumbs up? Does everyone understand that? Because we get lost right here. Okay? Because people will start to say, well, Ms. Lara, we already know 69.5 is the K shell that's only in the tungsten atom. We are not made of tungsten. Got it? Good. So we're also going to describe classical interaction. That's just going to be the first one. We're actually going to be talking about different types: photoelectric and Compton, photodisintegration and pair production. Okay, so we're going to be talking about different interactions. However, I'm going to focus on these two, because these two, can anyone tell me right now why these two are significant?
They're involved with scatter radiation.
Yeah, but they're a little bit more.
They're in the diagnostic range of what we use.
They are considerable interactions that happen within our diagnostic range. So thank you very much. I want to make sure that we focus on that, and because that's where we're going to be spending a lot of time. Yes, photodisintegration is important. Yes, pair production is important, but we won't see that in our line of field. Does anyone remember what our diagnostic range is?
30 to 150.
Besides Daniel and John?
Was it 30 to 150?
Oh, I'm sorry, one? Go ahead, Isbedi.
Oh, I thought it was 30 to 150.
30 to 150, thank you. All right. Very good. Okay, so differentiate between X-ray absorption. These are going to be two huge words. Huge words. Absorption and transmission. So if I were you, I would already understand what those mean and explain differential absorption, because this is going to be a huge concept. And when we start talking about our energy levels, and we start talking about matter, the atomic number of matters between bone, water, soft tissue, and air, this is going to create our image. Okay, so these are huge concepts, but we're going to start with types of interactions first. Any questions before we move on? So here we're talking exactly what I've mentioned. Here is the primary beam. This is the primary beam, the beam that's exiting from the tube. Okay? Now, when it interacts, I don't need you to memorize this film, because we're going to get into all of these words. But when these primary beams, see the symbol? The symbol means what, Jessley? What does the symbol mean? What? Photons, good. So this symbol right here, so we know this is, we're talking about X-rays or photons. This is the symbol. So as these photons enter the body, we know that there's going to be some type of interaction. We know that there's going to be an interaction. But we have to understand these interactions because we want to minimize harm to the patient. One, always. And at the same time, while we minimize harm to the patient, we want to produce those better quality images. Okay? So too much KVP or too little MA is not going to allow us to produce those quality image. Make sense? Good. Now, review here. Who can tell me what causes more patient dose? MA increase or KVP increase?
MA.
Thank you, Daniel. MA. Awesome. We're on fire today. Love it. So, X-ray interactions with the human tissue. When we are emitting and our primary beam is right here and we place collimate over our objective, there is types of interaction that's happening with the soft tissue. Around the anatomy, we know that nothing is happening, and we're going to talk about that. Nothing is happening because this is interactions with air and the image receptor. But here we have interactions with soft tissue. Here we have interactions with muscle. Here we have interactions with the fracture of the bone, right? What kind of fracture is this?
That is splintered fracture.
What kind of fracture?
Splintered.
It looks splintered. Thank you, Amy. Very good. You see, we're putting it together. So exciting. We're putting it together. You guys are seeing that. I love it. So we're having interactions with the bone. We're having interactions. So as you can start to see, not all interactions are the same, are they? The radiation is interacting with different parts of the human tissue differently. Make sense? So all of this is matter. All of it is matter. But because calcium is there, it's not in the tissue, it starts to change what we see because of the interactions with X-rays. So we're about to dive into X-ray interaction, I can't say this enough, with human tissue. Got it? Yes, Miss Laura. So, of those interactions of X-ray, there are five of them that can happen, okay? However, only 2 of them are in our diagnostic range, okay? One falls below our diagnostic range or at the lower end of our diagnostic range, which is classical interactions. Compton scattering and photoelectric fall within our diagnostic range. Pair production and photodisintegration fall out beyond 150 keV, okay? Pair production and photodisintegration actually fall within the million electron volts, not 1,000 kilo, but million. So that's definitely outside of our diagnostic range, okay? So it says right here, the first 3 occur within the range of energy in diagnostic radiography. But again, this is on the lower end of our spectrum, of our range, and it does not contribute to image formation. Okay? Questions there. So we have 5: classical, Compton scattering, photoelectric effect, pair production, and photodisintegration. Any questions there? No? Okay. So let's get into classical interactions. It has some also known as names, so it's also AKA Coherent and Thompson. Okay? Coherent and Thompson scattering. You may hear about Compton scattering and Thompson scattering. They do not have the same effect. Okay, and we will talk about that. So the incident X-ray photon, where do we find this incident X-ray photon again, Jolie? Where are we going to find this X-ray incident? Where is it coming from?
Is a cathode.
It's coming from our primary beam, right?
Yes.
From our primary beam, and it is going to collide with an atom of the tissue. So there are a couple of things that happen in classical interaction. Because this is so low of energy, it does not possess a lot of energy. What is the rule of thumb average of our energy of our primary beam, Luke? What is the rule of thumb of our primary energy? What is the most abundant keV value of our primary beam?
Like the 69.570.
Remember, we're not talking tungsten anymore. Don't mean anything anymore to us. We are outside of the truth. So if I set a KVP of 100, what is the average energy of our primary beam? It's a rule of thumb. You remember?
Nah,
Oh, okay, no problem. John, help them out.
Isn't it a third of the KVP?
1/3 of the KVP. So if you have 100 KVP chosen, then it's going to be roughly about 33 keV that is going to be the most abundant photon. Make sense? So even then, the lower you choose your KVP, the lower your value is, the most abundant photons are. So if they do not have the ability to ionize, which is Coherent and Thompson, does not ionize, it transfers its energy and excites these orbiting electrons. We've heard that word before, excite, Sharon. We heard about excitation in the X-ray tube. When an incident electron came in and excited an orbiting electron, the orbiting electron had to give off or transfer its energy in the form of what, Sharon?
Heat.
Beautiful. Heat. However, in this interaction, the incident photon excites an electron, and the electron has to give away or transfer that excited form in a form of a low-grade photon. Super low-grade photon. So the incident photon from the primary comes in, excites an orbiting electron, and that orbiting electron that is excited has to transfer that excitation in the form or release another bundle of energy or photon. And it is so low that it doesn't do anything to produce an image. What it basically does, it contributes to patient dose. So let's see if we can't put this here. Let's put it in form. Coherent scattering. This is why it's called scattering. Scattering because here's the direction of the primary X-ray, right? Ideally, if we're pointing, where do we point, Wani, our X-ray tube to? Where do we aim our X-ray tube to?
Like what
Where
the
do we
tube is
aim?
aiming?
Yeah, where do we aim our X-ray tube? Which way? Where do we aim it to? If
Through the patient?
To the patient, but where do we place our patient to?
In the table.
Okay, but where do we place? What do we place behind our patient or in front of our patient? What's going to capture the X-ray, Wani?
What's gonna catch the X-ray?
Yeah. What produces the radiograph?
The tube.
Okay. Okay. So, when you go to lab, Wani, walk me through lab. This is probably when you go and you position your lab partner for a chest, where do you place them?
In the wall unit.
Okay, what's on the wall unit? What are you going to put inside of the wall unit?
The cassette.
What is the cassette for?
To produce the image.
There we go.
I'm sorry.
So what do we call that? The image receptor, right? So we aim our tube, we aim our primary beam to the image receptor. Okay? So we know by looking at where our X-ray is coming in, where our image receptor should relatively be. Make sense? Yes? Everyone understand that? But what happened is, and this is where that scattering word comes from, here comes our incident X-ray. Here is our image receptor. But remember, this incident photon or X-ray collided, let me go with this one, collided and excited this electron. It excited. So this incident photon gave up its energy to here. This electron absorbed it, and it released it in a form of a low-grade photon. But guess what? It has now gone a different direction. When a photon goes in a different direction of what it is intended, that is called scattering. If the photon direction is no longer towards the image receptor, it is called scattering. So Thomson scattering is correct because this photon, even though it gave up its energy, is no longer going to, and then the energy that was converted is no longer going to reach the image receptor. Make sense? This photon is actually going to go on and contribute to patient dose. It is not going to contribute to image formation, but contribute to patient dose. So this is why we don't always go low on our KV, because the lower we go, we are going to start producing more excitation than ionization. And then we need ionization. Okay, so let's take a look at this chart. Let's go back and put it in words. And coherent scattering, Compton scattering, and coherent scattering, classical interactions, or Compton scattering, same thing. Low energy photons come in, okay? They do not ionize. Nothing is being removed. And coherent or classical interactions, nothing is being removed, and they do not contribute to the image. However, they do interact with tissue atoms. This is an atom of the side of the body. And they transfer the energy, causing electrons to vibrate, excitation, right? Releasing that excited energy in a new direction. There is your scatter. Got it? I'm going to stop there and let you guys marinate for just a second. I really want to finish Compton scattering today. No question. You have this in PowerPoint. You shouldn't be writing this down. This is all in your PowerPoint. Go ahead, Jonathan.
So this one, it doesn't ionize anything.
No.
All it does is scatter it off in a different direction. How does it?
This photon comes in, right? Excites. The electron that's in the orbit absorbs, and it's going to vibrate and release that energy, another photon, in a different direction.
Okay, so when you say it absorbs it, so is that? Because I guess what I'm trying to understand is how does it actually? Well, two things I'm trying to understand. How does it actually add into patient dose if the energy is just absorbed but then released immediately?
The electron, it absorbs that. Now remember, an electron has to stay in a ground state. It cannot possess any more energy in order to continue in its orbital state, in its orbital rotation state. So if it's vibrating, it's containing enough energy that it has to release it. So it's releasing it in an energy state form. Because when you think of vibration, you're thinking of energy being released from that movement. So that's exactly what's happening. It's not strong enough to deposit itself or have the energy enough to continue to travel to the image receptor. So it's just going to get absorbed, transferring that energy into the adjacent tissue where it does not continue to vibrate, if that makes any sense. Keep going with
that makes sense.
Okay. It's just going to continue until all of the energy that can be absorbed without causing excitation or changing that orbital ground state. Does that make sense? So let's just say. So it does.
So it's going to lose a little bit of energy with each interaction. Like with each time each time it goes to the electron, it gets absorbed. It's going to lose a little bit. So a little bit of energy is absorbed in.
Yes.
But just not enough to do anything.
It's not going to be equal. No. Anytime you have an incident, collision, or excitation, you're depositing an energy. Now, it's not going to be equivalent. What comes in is not equivalent to what goes out.
Okay.
Okay? Until it diminishes.
Okay, that makes sense. I think the book it said something different. It said something. What did it say? It said. What did it say? Oh yeah, it said the scatter photon is equal energy as the incident photon. That's what was confusing me, because it seemed like it was saying like it's not losing any energy at all.
But it has to. Even if it came off to the microns, just to say it's equivalent, it has to, because it's never going to leave the patient. It eventually has to spend its energy in the form of travel. So let's just go with the book. Even if it's equally distant, let's just say this energy is not far to travel deep within the patient. It is eventually going to settle in and disappear in an absorbed matter inside of the patient. It's never going to contribute or leave. It does not possess that enough energy. It's like saying I had enough energy to run a mile, not 20. And so you're eventually going to settle. That energy will be absorbed. Whether it's, I do see what you're saying. I have another source that says no, they're not equal, because any interaction is going to reduce that. But if it's close to that 0.0001 of equality, I'm not going to worry about it. But it's eventually going to settle. The most important thing I want you to know is that the incident photon is no longer going to reach the image receptor, but settle into the patient, into the next atom that's here, and then the next atom that's here, and then the next atom that's here. It's going to continue on that same.
Okay, that makes sense.
Okay.
Thank you.
Any other questions about classical scattering? Yeah.
Just clarification. Is the incident photon hits electron in tissue? Is another photon produced, or is that one just scattered?
One more time, John.
When the incident photon's coming in and it hits the electron in tissue, right? In a matter, does it gets excited and produces heat? Is that incident photon scattered? Like, does it go off in another direction, or is a new one produced? It goes off in a different direction. New photon produced.
It says, okay, so it says because the energy is re-emitted in a new direction, the way that it is explained, so right here, instead of the atom absorbing the energy of this X-ray photon causing excitation, and then it immediately releases the energy. So but the energy is released in a new direction, so no heat in the matter. We're talking about an excited state, and we think of a vibrating state, because we're going to also talk about when we get into digital imaging, when an electron is excited, it contains that. It looks like it's vibrating. It's a hyper or excited state. I guess to answer your question, John, is to say the incident photon that has come in and excited the atom, that energy has to be immediate release from that atom in order to keep it keep it grounded, to keep it without having it more excited. I'm losing my words. So the electrons get excited.
It wants to stop being excited.
They have to stop being excited. So that's like saying that the analogy that I use, when you listen to music, you dance. It's a stimulant. It's energy that's converting into another energy. It's just a transfer of energy. It's just a conversion of energy. So how did we get kinetic energy to convert over to X-ray? Well, we know that interaction. Here, how did we get coherent scattering to convert into another energy? It's really the same energy. There's really no conversion. We have photon coming in, we have excitation, and we have a photon going out, period. It has to be a release of that energy. The energy is so low that it is not going to contribute. I don't want to get stuck here, because this is insignificant to the sense that it's energy coming in, excitation happens, energy goes out in another direction. Does that make sense? I'd rather have more time where we're going to be able to talk about Compton and photoelectric. Okay, but it's just energy in, excitation, energy out, no ionization. Okay, so let's kind of move from there, because I really want to get into Compton where we have ionization. Okay, yes, okay, all right. So moving on. So here is the critical concept that you guys should be paying attention to in your chapter. Always, always, always. We have scattering events. These scattering events do not lead to image formation. These scattering events do not lead to image formation, but they do lead to increased patient dose, slightly. Because the patient, even though it's atoms, this, and the tissue is created of atoms, that energy eventually settles within those atoms inside of the tissue to be quantified by, how do we quantify patient dose? What unit of measure do we use for patient dose? Anyone?
Grams.
REMS?
Rad.
REMS would be for our, and I really should stick to SI, but REMS would be for our occupational dose.
Rad or gray?
Rad or gray. Perfect. But thank you, Daniel, for jumping in there. REM is occupational dose. When we're talking about patient dose, we're talking rad for the conventional and gray for SI. So I really should be more specific because I think the new content specifications for the ART just came out, and they are moving totally towards SI units. Not for your exam when you guys graduate, but for the class that's coming in, I'm going to be talking strictly SI from now on. Okay, so I might as well get into the habit of it. So grays, perfect. So classical interaction, Compton scattering, coherent interactions, they all contribute to slight patient dose. No image, but patient dose. Got it? There is another type of scattering that we're going to talk about. This is Compton scatter. Compton scatter. This is an interaction with human tissue. So when we're talking about Compton scatter, here we have it. It is most responsible of the scatter radiation produced during radiologic procedures. So we already know an incident photon is coming in. However, if you can see in this image that I have here for you, an incident photon is coming in. An incident photon or a photon is also emerging. But what else is happening right here? What is that?
Scattering energy?
It is scattering energy. This is the scatter photon in, and it's going in a different direction. But what is this?
Ionization.
Ionization. Thank you. An electron is going out. So Compton scatter does ionize. It is an electron out. Not only is the incident photon coming in one direction towards the image receptor and now has changed directions. This is different from Thomson scattering because we talked about incident photon coming in, this atom becoming excited or the electrons becoming excited, and another energy emerges. Whether slightly lower, depending on the two, but I'm going to stay with yours. Equal energy. Either way, it does not leave the patient. And Compton scattering does. It has a higher KeV range. This is where we'll usually find those Compton scattering, and it'll increase. So we're going to be very paying attention to the type of KeV that we use. And why are we talking about KVP? Who wants to tell me, besides John, and why are we talking more about KVP here? What is the word that I started out this whole lesson with?
Primary beam.
Primary beam. I said primary beam.
Ionization.
Which one?
Ionization.
Okay, good. I'm still looking for something else.
You started with John talking about the waves and.
I did. Where is
Did you just speak with the sine waves or something?
Sine. But I want to put it right here. What is this?
Energy?
And what determines my energy of my photons, of my incident photons?
KVP.
Tell me KVP. Thank you. The energy of my photons is KVP. It controls the energy of my photons is KVP. So everything that I'm talking about and increasing is my energy level, which is controlled by KVP. Make sense? So if we're talking about the diagnostic range of my primary beam in KeV, that's how much the photon energy is, it's regulated by my technical primary factor, KVP. Everyone got that? Good. Perfect. So here comes Compton. Now we're talking about Compton, right? We have an incident X-ray from my primary beam, enters a tissue atom, interacts with, and I put this in here, outer. Most of your resources will say an outer shell electron. However, in your book, it'll say middle to outer. Got it? Middle to outer. If it's in the middle and it's ionized, we know that we're going to have secondary or characteristic radiation form. What is characteristic radiation, Maricela?
I'm sorry, what was the question?
What is characteristic radiation?
Whenever an an incident electron comes in, interacts with the orbital electron, and causes ionization, then leading to the cascading effect.
Perfect. But instead, on this one, we're not starting with an incident electron. That was in the tube. Here we have an incident photon comes in. If it interacts with a middle shell orbit, we know that this one is going to fall in its place. And when it falls in its place, a photon will emerge, correct? Yes, we've already discussed that, whether it's happening in matter or whether it's happening in tungsten atoms. Questions? I see a lot of like, what? What did she say? So let me pose the question this way. If an incident photon comes in and knocks out an outer shell, the most outer shell electron, cascading won't happen, will it? Yes, no?
No.
It won't happen. But if we knock out a middle shell electron, we know what's going to happen. An outer shell electron will drop and then will release another photon, correct? Yes? Perfect. So when I see this, an incident X-ray photon enters a tissue atom, interacts with an outer or middle, but more outer orbital electron, and removes it, ejects it from its shell. It loses up to 1/3 of its energy. What lost 1/3 of its energy, Pamela?
What was the question?
It loses up to 1/3 of its energy. What lost 1/3 of its energy?
Photon.
The photon. The photon that came in, correct? That we now named incident photon. Lost 1/3 of its energy. But pay attention, look. So look, now we have this incident high energy photon. It came in, whether this one, that one, doesn't matter. It came in. It now changed directions because it collided. Now we're going to have something else happen because this electron has now possesses kinetic energy. It's now in motion. It has been knocked out of its binding energy and it's now ejected. It's ionized, right? It's removed. It's going to continue. It has its own story. It has its own journey. And we're going to talk about that. But the incident photon now changes direction. It has lost some of its energy, and it can continue, depending on how much energy it has, it can continue the same process, more Compton scattering. Does everyone see that? Until this energy finally does one of three things. It's going to either get absorbed by the patient. It's either going to leave the patient and get absorbed by the who? Who else could absorb this photon? A technologist, or it can find its way to the image receptor, and that's what we're going to talk about. So there's a lot of things that this photon, unlike classical interaction, because what happened, Ruth, in the classical interaction photon, where did that bundle of energy eventually stay?
In the patient?
In the patient. In the patient. Never emerged from the patient to affect the radiographer or ever land on the image receptor. Make sense? But we've moved up the diagnostic energy level. And so this photon that initially started the entire sequence, here, we haven't even talked about the secondary or characteristic photon that is going to emerge, right? We still have some more discovery. So this image is a little bit dark, but I want you to get an idea of what's coming in. Here's our symbol. Here's our incident photon, putting a little bit of color, making the eyes come to light again. Here we had an electron. It has now been removed. It is now in possession of kinetic energy. This electron now has a new name. What do you think the name is? And why do you think it has that name?
Photoelectric?
It's not photoelectric. We're on Compton.
Oh, sorry.
But you're on the right path, Tracy. Why does this electron is now being called a Compton electron?
Because it was the ejected electron?
It's the ejected electron. You're absolutely right, Amy. Through which type of interaction?
Compton scattering?
What interaction are we talking about right here?
Compton?
The Compton interaction.
Compton interaction.
Correct. The Compton interaction. So because we are talking about a Compton interaction,
It's Compton
the
scattering.
electron that now possesses kinetic energy is going to take the name of the type of interaction that it just happened. Just like the Brem X-ray takes on the name for bremstrolon because that was the type of interaction. The characteristic X-ray takes on that name because of the type of interaction that it emerged from. So nothing different. Okay, so we have an incident photon coming in. It ejects an electron. This electron now possesses kinetic energy. This electron has a new name now. It is no longer KLM electron. It is now on its own Compton electron. Okay? The incident photon that collided with that Compton electron and sent it in motion now loses some of its energy, and it now takes on a new name. This new name is now called the scattered photon or Compton scattered photon because of the interaction. So we had one incident photon, two effects. Make sense? So what can this scattered photon continue to do? I just went over it, Shibu. What can one of the things that this now new Compton scatter photon, what can it do now?
It may
It can do one of three things.
it will go to the image receptor.
It can go to the image receptor. Thank you. What else?
And it can go to the technologist, means who is standing.
Number two, perfect. And what else?
And three, it may go to some other, it may hit some other atom in the body.
It stays inside the patient. It gets absorbed by the patient. Good. Perfect. What is the unit of measure for if this scattered photon, Stephanie, is now going to affect the worker, the occupational worker, the radiographer, the technologist? Give it to me an SI. The unit of measure for occupational dose.
It'll be the server.
Sievert, there you go. Good job, my people. I'm loving it. Thank you. So I can tell you this picture tells a lot, doesn't it? This picture tells you what type of interaction we're talking about, right? We know that this is not classical. This is not coherent because an electron was removed. So it cannot be Compton scattering, could it? You see where I'm going with this? I'm starting to give y'all x-rays and identify fractures. I'm going to start giving you images to identify interactions. Make sense? Good. Perfect. So, moving on. Now, this interaction, we're not talking about just the incident photon. We're not talking about the Compton photon. And we're not just talking about the Compton electron. We're talking about the entire interaction. So, it ionizes. This interaction does ionize, correct? And when we ionize, we make an unstable atom. Son, what is the new charge of this atom that has had an electron removed? What is the new charge of the atom? If an electron is removed from an atom, what is the new charge? Right here.
Positive charge?
It is a positive charge. It's in need of an electron to go back to become stable. Okay? So the harm here, when we have an ionized atom, the ionized atom, by the natural laws of physics, it needs to go back to a neutral state. A grounded state is the way that we would say it. A grounded, balanced state. So it's looking for an electron to make it grounded again. However, when we go into the future and we start talking about the possible toxic types of combinations that can happen when we have a positive charged atom looking for another electron to stabilize it, it can create a toxic molecule. Okay? But that's in the future. More to come, more fascination to come. The ionized atom, making it unstable, produces those secondary type photons. What is a secondary or characteristic photon? Right? The secondary or characteristic photon. If the Compton interaction ejected what kind of orbital electron to create a characteristic photon? I'm asking a question to anyone.
Is it when it injects the middle, one of the middle ones?
Absolutely. So it is possible. So we understand this. Anytime we eject anything that is middle, an electrical outer orbit electron is going to drop down. It happens. In that dropping, we know that photons emerge. They are characteristic or sometimes called secondary photons, okay, because of the interaction. Perfect. If an electron hits, the incident photon hits an outer shell electron, then this does not happen. Make sense? No formation of secondary photons. All right, number 2. The ejected electron, remember now it has a name. The ejected electron now has a name, Compton electron. or sometimes called the secondary electron, but let's just stick with Compton electron, leaves the atom with enough kinetic energy to go through interactions of its own with adjacent atoms. What kind of interactions do you think that could be? Anyone? What kind of?
Brems?
Huh?
Brems.
Could. Possibly, but we're going to stick to Brems inside of the two because I don't want to confuse, but I do. So what happens if this Compton electron ejects another outer shell electron?
You create another characteristic
We just
photon.
create another ionization and more kinetic energy until those electrons start to settle. But what happens if this Compton electron hits a middle shell orbital electron? Then we start to have photons emerge. You see where the process can happen? Anytime you have a Compton electron that possesses energy, motion, we can have other interactions that happen. Make sense? Yes? No? Talk to me, people. We're moving along. And I see some arms crossing and some faces kind of, okay, this is what we're getting to. And it takes a little bit to wrap your head around. All right, so we talked about the atom, the entire atom, tissue atom becomes unstable. That's through Compton interactions, true. The Compton electron possesses kinetic energy and can create its own interaction within the human tissue. We know that that's true. But we also know that the incident photon that initially started this entire Compton interaction, which is now called the Compton scatter photon, can do one of two things. Well, three things. It's just not on here, but three things. Can continue on and produce other interactions in the tissue, right? Knock out another outer orbital electron because it got scattered, right? It's now going in a different direction. But if it's close enough, it can still leave the patient and interact with the image receptor. We're going to know this as the word fog. So the Compton scattered photon can either continue on with other interactions with other atoms of tissue, nearby atoms, or it can reach the image receptor and contribute to the image receptor, but it's going to take on the name fog. So let's take a look. Let's recap. Here is an outer shell electron. We don't know what kind of atom this is. We'd have to go back and count the electrons to tell us what kind of atom this is. Here comes the incident photon from the primary beam. It ejects an emitted electron. This electron is now called what?
Compton electron?
It is now called the Compton electron. This photon is now going to change directions and has the potential, let's just draw a line. So now this is going to change directions. How come it's not letting me? There it goes. And it's going to go this way. So what is this photon now called?
Compton scatter?
Scattered electron? No.
Scatter?
The Compton scattered photon.
Compton scattered, because now it's going in a different direction. Where would our image receptor be? Over here, right? Because this is where we're aiming our primary tube, aren't we? Yes? Good. So now this is a scattered photon, now takes on the name Compton scattered photon, and it has the ability to go do what? Three things. We talked about two of them in this last slide.
The patient absorbs it.
The patient absorbs it.
The back. the technology.
The tech can absorb it.
Technologist absorbs it.
Or it can go to the IR.
So it can go to the IR, the fog. Another thing that it continued to also do, remember, this is going to continue on and start causing and interact with other electrons from another orbit, right? So on and so forth. But this, depending on how much energy, it could probably also knock out another electron. Make sense? So this, depending on the energy level that it has, can do multiple byproducts of this one interaction. Does everyone understand that? Okay? So if our incident photon is coming in this way, we know that our image receptor is this way. We know that because we only aim towards our image receptor. We place our body in front of the image receptor. Make sense? When the incident photon collides, we know that the photon that collided will eventually change direction. Now, again, why is this called Compton? Why did we call this the Compton interaction? What did Compton say the interaction was with specifically? Which electrons?
The outer orbital.
Outer or middle. So if I know that we are going to have interactions with the middle or outer, we are talking about Compton only. So these byproducts, whether we're talking about the patient, whether we're talking about the patient, let me go back to my slide. Whether we're talking about the interactions with other tissue, exit the fog, contribute to the patient dose, or contribute to the occupational worker, all of that started with one incident photon. Does everyone understand that? And that incident photon collided with an middle or outer shell electron. Make sense? So all of these are considered byproducts of that interaction. When we get to photoelectric effect, it does not have the same byproducts. Or I think one of my students yesterday said side effects. Does not have the side effects that Compton does. Make sense? So, we talked about image fog, remember? If the Compton scattered photon strikes the image receptor in the wrong place, it will result as image fog. So remember, our incident photon was intended to hit the image receptor. The image receptor right here. So if this is my image receptor, this photon was going to hit my image receptor right here. I'm trying to get better at this. Hold on one second. Okay, here we go. Okay. So this photon was supposed to hit my image receptor right here. But remember, if it got scattered, it hit my image receptor right here. What would be non-useful about that? What would be non-useful about having this photon deposit its energy onto the image receptor over here? The one thing I can tell you is that if it intended and I had pathology here, but it would never went through it, and it landed over here, would we be able to identify that pathology that was over here located on this section of the patient? We wouldn't. So when we have scattered photons, they don't produce anatomic useful information. They don't. They just deposit energy, random energy and we'll talk about what that random energy is.
Miss Laura, is that what ends up looking like fog?
It starts looking like fog. Yes, absolutely. And that's why it's called image fog. Okay?
So when you say fog, to me, is it just like it looks cloudy in certain spots?
Let's take a look. Oops. Well, when you think of fog, you think of like this, right? You think of fog, something like this, but it's the same concept. This. If you take a look at this image right here, kind of hard to see, but you see this chest? It kind of looks like it has a lot of haze over it. It doesn't really look like it is supposed to. It doesn't look clear. It looks kind of, oh, this is a perfect one. I don't think it allows me to see it, but you can see, it won't let me move it. I don't know if you can see it, but you can see the difference. It's almost like a blanket of fog on it. I'll get some better images for you so that you can see it. Okay? All right, so let me go back here. So we are here. We talked about this. We're almost done with Compton. When we think about Compton, we talk about if the if the scattered photon strikes the image receptor, like I said, it's not going to be in the right place where it was initially pointed at or aimed at. This is what image fog. We should minimize image fog as much as possible. It is undesirable. It takes away from the quality of the image. Remember, it takes away from the quality of the image. So we have to keep in mind how much radiation energy we choose for our primary beam, because we want to limit this fog. This is your 2 years of education. It's not pressing a button. It's taking your photon energy and making sure it is desirable. Okay? So one of the big, huge, I'm going to leave you with, huge, before my microphone goes out. When we're talking about, because this atomic number, we've heard that word before, those words before, atomic number. Where have you heard those words before? Anyone?
Periodic table.
The periodic table. And we've talked about the atomic number of tungsten, which is?
74.
69. 69.
74. 69.5, Daniel, is the K shell binding energy
74. That's right.
of tungsten.
My bad.
Oh, no worries, no worries. So we've had a lot of numbers. So when we're talking about atomic number, we don't know unless we specifically say calcium for bone, soft tissue, which is a combination of a lot of different types of tissue, muscle. So our Compton interactions are not going to be dependent on our body. What it is going to be dependent on is related to the energy. Energy of the photon. What controls the energy of the photon?
KVP.
Thank you. So here we go. This is the slide. This is the slide where I say connect concepts. Connect concepts. As X-ray energy photon, the X-ray photon, whatever, same thing, energy increases. The probability of the photon penetrating in a given tissue without interaction also increases. That is the definition of transmission. When the X-ray photon or the photon penetrates the body without Compton interaction, that is transmission. Okay? However, we just said it. If the photon energy increases, it will likely increase Compton interactions. So, what does this basically say? Because you're just saying, well, Ms. Lara, you just told me in this sentence up here, increasing the KVP increases transmission. True. Absolutely true. Without any Compton interaction so far, because we're going to be talking about Compton and photoelectric effect. But here I go back and say, well, hold on. If I increase the KVP or photon energy, I'm likely going to increase my Compton interactions or my Compton scattering. That is also true. Because we started out with, what is the energy range for Compton? What is the energy range for likely to happen with Compton? Between 20 to 40 keV, right? If I have 100 kVp, what is that range again? What is the KeV most abundant inside of my primary beam? 33. 33, does that fall within that range? So as my KVP increases, Compton interactions increase. Okay? As my KVP increases too, transmission also increases. So how do I say that in a nutshell? As KVP increases, both Compton interaction and transmission increase. Okay? Questions?
So that's just up to a certain point then, though, right? So, like, say I increase the KVP to 150. Well, now I'm not going to have any Compton interactions.
Well, that's just a guide. That's just a guide. So if you have 150, let me do my math on 150. So you're talking about an energy level of about 50. That's that. An energy level of about 50, right? You're just barely going outside of it. So don't take it as an absolute. Don't take it as an absolute because you're barely going 10 over the relative range for Compton interactions. It's not absolute.
Okay, that makes sense.
So right now, this is the huge one. This is what I need you to know. When we start talking about increasing KVP, yeah, we're going to increase transmission. However, some photons are going to continue high probability of Compton interaction. And we already know the byproducts of Compton interactions. So when you guys go home today, when you study today, sorry, long day. When you go and study today, I want you to start paying attention to the byproducts of Compton interaction. We had zero. We had really zero with Thomson scattering. Thomson scattering excited, didn't ionize. Energy went in, energy emerged. Okay, it settled in the patient, contributed to patient dose. That's the one side effect of Thomson scattering. Here we talked about fog, patient dose, occupational dose, and don't even get started on the Compton electron, right? Because the Compton electron is often doing its own thing. Because what kind of energy does the Compton electron have?
Kinetic.
So as we're finishing up this section, Compton scatter photons retain about 2/3. After they've collided with the middle or outer shell electron, they contain about 2/3 of their energy before they were the incident photon and may exit the patient to expose the radiographer. This is why we have to be shielded. Patients absorb and get x-rays are going in. They're causing some type of interactions. And then we know that there's going to be scatter. We already know. So photons are emerging from this patient. And so therefore we shield our vital organs. Make sense? Yes, Miss Laura. Okay, I'm going to stop there before we get into the wonderful world of photoelectric interactions. Questions?
Ms. Laura, before on that same section in the book where it says that the scatter photon retains about 2/3, there's a section about talking about degrees, about the 0 degree.
So it says from 0 degree. So if you are, it's a 0 degree deflection. So if you bounce a ball, chances are that it's going to go back in the same direction that it entered in is not likely going to happen, right? It's not going to bounce back or change direction to where it originally started. So it's talking about the 180-degree range of where it can scatter when it interacts with that electron. Okay, it's not always going to come in and go the same direction every time. It's just not, it can change directions up to 180 degrees. Okay, so stuff, wonderful stuff, right? Go back and read it. Go back and read it and read photoelectric absorption, because photoelectric absorption can be a little bit more complex. Okay? Yes, Johnny?
Can we go back to image fog a little bit? So just, I'm trying to make sure I understand it right. So as it's now become a scattered photon, it's coming. It was supposed to hit the image, the IR up here, but it hits it down here. So it's scattered, so it's coming at this diagonal angle, right?
Right.
I'm sorry?
You're cutting off a little bit, but okay.
Breaking up?
Yeah. But so let me go back real quick, and before I lose my microphone.
I think I lost you.
Can you guys still hear me? Hold on.
Yes.
Okay, thank you. So, okay, so let me go back and share this. Okay, right here. Okay, so if we have a photon that is coming here and here, right? Let's just say, let's just go to the break. Can you hear me, John? Johnnon? Okay, so if we have a photon that's coming into the break, but it had Compton interactions, and it gets deposited over here. Now this is leaving the patient. This is leaving the patient, right? Yes. So if we went right in between this break, let's just say our photons are coming in and it's right in between this break. It did not run into any bone. It did not run into any bone. It was actually at the part of the joint where we know we should have a dark color right here on that image receptor. Make sense? But if it didn't reach the image receptor where it was intended to reach, it deposited that information that it's supposed to be dark on the image, and it deposited its way down here. It's inconclusive. We wouldn't expect a dark image to be on a bone or a dark energy. And so we'll talk about it. It's very small, and sometimes it's very insignificant. But when you start to see a blanket of fog, it becomes very degrading. You start to lose focus of sharp images. So when you see something like this, the image of fog, yes, we know Compton scatter happened. A lot of Compton scatter happened. So how do we go back and reduce it so that we can improve our image quality? So fog is not representing its information. It's photon energy depositing onto the image. It's like pancake mix. If you just drop pancake mix on a surface, it's just going to splot right there. But if you were going to make a picture of different colored pancake mix, let's just say you had blues and you're going to do the flag, right? Red, white, and blue. And if you took that blue and you put it somewhere on the red, you know that scatter happened right there, because it's not intended to have. That was supposed to be red. It's going to make more sense, I promise. Let me just try to figure out how to articulate it. But when you think about fog, you think about deposits of energy, because it's energy, it's photons. So photons deposited on different parts of your image receptor, and it becomes unuseful. It degrades the entire image. It's like a blanket of fog. Okay, and we can control that with the use of grids. Eventually, we'll control it with the use of grids. Okay, that's just more fun to come, but not this semester. We don't get into grids, I don't believe, this semester. Okay, so I'm gonna leave y'all there. Go through Compton, because I'm still gotta go through photoelectric electric, and so you have the slides. Make sure that I'm going to be adding to these slides, so you make sure you add on to your slides as well, okay? And start reading ahead, because we can see just by this picture, we're not talking Compton anymore. We're going to be going into the inner shell electron. Outer shell, middle outer shell, and then the inner shell. Okay? Yes? If you guys can get through Grimm and characteristics, this is in the bag, but just make sure you go through it. Got it? Any questions for me? No? All right. I'll see you guys. Go ahead. No questions? I'm going to wait. I don't want to cut anyone off. Going once. Going twice. 3 times. All right, guys. Y'all have a good one. Bye.